Okay, so kind of going back to kind of what we did last time. So I'm going to kind of jump into SolidWorks today and kind of go into kind of how to set up these simulations. So for anyone who hasn't used SolidWorks before, I believe there are a couple people. What I'm going to do is just kind of basically when you open SolidWorks, this is going to be your general user interface. I'm running 2023 right now. I believe the latest is 24. This will look identical, or it should anyway. So what I'm going to do is I'm going to start just by opening a new part file. Typically, when you're doing a simulation, you'll already have some geometry. So I'll probably model something up quick just so we have something to kind of work with. So I'm going to go here to part inch. I do have these templates already set up. If you don't have templates, you can always go over here to novice and then just select whatever file you need. But since I have some templates with different units, I'll go ahead and just pick one of those. So I'll just pick, actually, I'll switch the units here to metric. If you, for some reason, open the, if you have a part file or assembly file with the wrong units, you can always go down to the bottom right-hand corner here and switch your units to, like, let's say IPS, from IPS, let's say inch pound second to MGS, millimeter gram second. So I'm going to switch it to that. And then what I'll do is I'm just going to go ahead and let's just go ahead and save this part file here real quick. So just go ahead and put this under downloads. I'll just call this like sample or something. Okay. Okay, so I went ahead and saved that. So this is your general user interface. Again, most of you are probably very familiar with SolidWorks. This is nothing new. So when you have a geometry, I'm going to just model up something here quick, just that we can work with. Something very similar to that kind of little L bracket I had last time. So for that, I'm just going to go to the front plane. This will probably be about the only modeling I'm going to do tonight. So I'll go to the front plane here. I'll go and sketch, and I'll just go ahead and sketch kind of sketching the side view. So just kind of sketch something along the lines of this. I'm just using the line tool here. And snap it back to here. So do something like that. A couple of things I'll do. I want a constant thickness, so I'll go ahead and hold down Control on my keyboard and select this line and make them equal. So put an equal relationship. So then they're equal. I'll also do the same equal for these two lines, just to kind of make it symmetric. And then I can actually go and put some dimensions in. So let's say, since we're in millimeters here, let's say this is 100 millimeters tall. That's about 4 inches. So that's 100 by 100. And then for the thickness, maybe we'll call it 10 millimeters or something. That's about half an inch thick. Maybe something like that. Okay, so we have that. Then I'll go over here to features, extrude. And then I'll go and extrude this. Since we're going to kind of have some symmetry here, I can, again, if anybody has any questions, please let me know about modeling. I'm going to, instead of doing blind, which is just pretty much extruding in one direction, I'm going to switch this to what's called midplane, which means it's going to extrude in both directions. So it'll keep that plane of symmetry down the middle. And let's call it, let's see what 100 looks like. Yeah, we'll call it 100. So 100 by 100 by 100 deep, and we'll go and do that. So go and save this real quick. Again, I talked about last time, you really, especially when doing simulations or when you're designing things, you don't want to have a sharp corner here because that'll induce a stress concentration. So I'll go to features here. Again, I could do this in the sketch as well, but I'll just do a fillet and kind of put a fillet on that corner there. But fillet, you'll just select select the edge and it'll put a fillet, and we can specify the radius. I'll do maybe 15 looks like. Yeah, I'll do like a 15 millimeter fillet. And again, this corner here is really not as bad. Again, I could put a fillet on it. I'll just leave that one sharp for now. Again, it's usually those inside corners that you really want to worry about. Not necessarily, again, you could put a small fillet here, but it's usually right there when this is trying to kind of get ripped apart that will cause problems. So go and do that. I'll go ahead and save. I'll hit Control S to save, which is always a good thing to do in SolidWorks. So we have this part here. I'll put a couple of holes. Maybe we're mounting this on the wall. Just to give us a little bit when I get into fixtures and stuff, to give us a few things that you can kind of, or we can kind of work through to kind of try different fixtures. So I'll just sketch on this face. And what I'll do is I'll sketch a center line from the origin. Again, you all probably are very familiar with this, but if you're not, please let me know. In a minute or two, I'll ask if you guys have any questions or anything. And I'll go ahead and put a circle here. And let's go and dimension this circle. So let's call it, yeah, let's call it 15 millimeters maybe diameter. And what I'll do is let's just go and dimension this. So from here to here, let's call it 25 millimeters maybe. And maybe the same from here to here. So we have that. Again, when you're in a sketch, obviously you want all of your lines and all of your sketch entities to be black, which means it's fully defined. You don't want them to be blue. If they're blue, that means they're underdefined. They can move around on you, which will kind of give you some issues or can give you some issues. So I've got that. Then what I'll do is, since we have symmetry here, I want to actually have two holes, one on this side, one on the other side. So I'm going to get out a smart dimension. In this case, since I only have one center line and one hole or one circle that I'm trying to mirror in this case, I can just hit Control A to select all. And then I'll just do a mirror entities command to mirror that hole to the other side. It's a quick way versus having to sketch it again. And then from there, I will do a feature. I'll go to features. I'll do an extrude cut. And I will do a through all, which pretty much just means it'll just go all the way through the part and go ahead and hit accept. And now we have two holes. Again, you could also use a tool here that's called Hole Wizard. If you're doing drawings, Hole Wizard's a little bit better of an option. But for something quick, extrude cut works a little bit. It's a little quicker, a little bit more simple to use. So that's why I kind of did it that way. So I'll go and save one more time. Does anybody have any questions so far about what I did so far in SolidWorks? Okay. Perfect. So next what I'll do is let's start getting into simulation. So you may or may not have simulation already added in. So simulation is an add-in into SolidWorks. So it's not, depending on how you have your SolidWorks set up, it may not be there by default. You may have to actually add it. So you have to add it. There's a couple ways of doing it. Obviously, I have quite a few tabs here. If you don't see some of these tabs, you can right-click and then go to tabs, and you can actually turn on and off which tabs you want to see. If you have this tab, I usually have this tab pinned here, the SolidWorks add-in tab, or SolidWorks add-ins. So what this will allow me to do, I can go here and I can see some of my add-ins. And to turn on simulation, I could just click this button right here. So it's a really quick and easy way to do it. You don't have this tab. Another way of doing this is you can go up to the options drop-down, go into add-ins, and then you can go all the way down to SolidWorks simulation. And what you can do is you can just check the box to turn it on. If you check the left box here, that'll turn it on just for this session of SolidWorks. If you were to close SolidWorks completely and reopen it, it would be off again. If you want it to always load in when you open SolidWorks, you can check both of these boxes, or you can check this box here for startup. So in this case, I will go ahead and I'll go ahead and check both of these. So this one's really not going to affect me right now until I close SolidWorks and reopen it. But this will actually turn SolidWorks simulation on. Same idea of just clicking this button here. So we'll go and turn that on, let it load. Sometimes it takes a second. Okay. And now you'll see what it actually did is it actually added a new tab here called simulation. So this is going to be our simulation tab that we're going to be doing most of the work on when we're doing our simulations. So first of all, when you're dealing with simulation, the first thing you want to do is do a new study. Again, I'm only going to be going over static studies today. And again, this probably is a bit of a review from everyone who's taken CAE. But for anyone who hasn't, this will probably be a good kind of overview of kind of what the basics are and kind of what you want to look for. So the easiest way, obviously, most of the stuff is going to be grayed out by default. You're going to go to new study. So when you go to new study, you can pretty much name your study here. I'll just leave it static 1. Typically, though, especially when you're doing research, it is a very good idea to actually name your study, something that gives you an idea of what you're dealing with. Especially in research, a lot of times what you'll do, I think I talked about this a little bit last time, you'll run a study with a kind of a coarse mesh, and then you might go back later with a fine mesh. So it's always good to have 2 studies and then say, I don't know, static 1 coarse, static 1 fine, so you know which study is which if you need to go back and change something or if you want to look at results from a study. So I'm just going to do a static study. I'm not going to really do anything else. Obviously, we do have the equivalent of SolidWorks Simulation Premium with the student edition, so we have a lot of things we can do. We'll probably get into some of those a little bit later in future sessions. So for now, I'll just leave this as static 1. I'll go ahead and hit accept. Okay, so we'll go ahead and hit save. So now we have the study. Your studies are also, when you're in simulation, your studies are also saved here at the bottom. So you have it where it says static 1. If you have multiple studies, you'll just see static 1, static 2, static 3 along the bottom. So far we have our feature tree here. this by default, this part has a material of plain carbon steel. So I can either change this here, or I can also change the material from within the study itself. So for now, what I'll do, I really don't need to look at my features too much. So I can just actually move. I can click on this little area here with that little dot, click and drag that all the way up. So I'm only looking at the simulation tree. This is what's called the simulation feature tree. So first, what I'll do, I'll leave it as plain carbon steel. That's fine. For today, it doesn't really matter too much about materials. So when you're looking at your tree here, again, this is probably a good review, but you typically want to go through this sequentially. So you're going to start at the top here, and then you're going to move down, further down, further down, further down. And then when you run, you'll end up with your results. So the first thing you want to look at is your material. Again, I'm not going to change the material, but I'll show you how to change it if you need to. Again, by default, simulation will pull the default material or the material that is assigned to the part. If you're doing an assembly, it'll pull the default material assigned to every part in the assembly. But again, within the simulation, you can modify all of that. So if I go ahead and bring that back up. So if you need to modify this within the assembly, you can right-click on this part right here. Right now, I only have what's called one body, which means I only have one solid body here. I don't have, let's say, several bodies within one part. So that's why I only see one thing here, and that is just called sample. If you had several bodies, you can actually, and I'll probably get into that maybe next time. Maybe if I have time today, I might get into that. But if you have several bodies, you can assign different material properties to different bodies. So that's a lot of times if you don't want to do an assembly, you want to have everything stored within one part, you can do that. But since we only have one body, I only have one thing to apply materials to. So I can right click on that. If I want to edit the material or apply a material if there isn't one, I can go here. It's going to open up. These are all the materials loaded into SolidWorks. I can also add custom materials. I'll probably go into that maybe in a future session of how, if you need to add a material that you find. I think I talked a little bit about MatWeb last time. If you find a material that you need, or if SolidWorks doesn't have a default material, you can go ahead and add it in there. So from there, again, I already have plain carbon steel. Another nice thing for material, I use the search tool a lot. So let's say you're looking for like aluminum or something, you just start typing AL. And you can kind of go to aluminum alloys. So you can kind of go under there. You can also go, let's say a popular one, if you do 6061, you can see it'll bring up kind of the aluminum alloys that you're dealing with. So that's a quick way to kind of get materials versus having to, kind of search under the categories. Again, either way works. And then once you select your material, you'll just hit apply. In this case, I already have plain carbon steel, so I don't need to apply anything. So I'll go ahead and close this dialog. So once your material is assigned, then you can kind of go down. Then the next option here, or next category, is what's called connections. Right now, in this specific study, I'm not going to have any connections. Connections is for what I was kind of talking about earlier, when you have multiple bodies, or if you have an assembly with multiple parts. So it's pretty much how every part or how every body interacts with other bodies. So if you have, let's say I bolted something onto these holes, and I wanted to model that. What I could do is I could say that maybe the part that's bolted on here is, let's say, what's called bonded, or it's fused to this face, or maybe it's not fused, it can move back and forth, but it can't penetrate this. So type of stuff like that. So I'll get into that as well in a bit, maybe the next session, or if I have some time today. So I'm not going to talk about really connections yet. We'll get into that. Next one you're going to definitely want to go into is fixtures. So fixtures, I obviously talked about that last time. Fixtures is pretty much how you fix your model. So this is a similar model to how the example I did last time, or that I had. So when you go into fixtures, what you can do is any of these categories you can just right click on, and it'll give you some options to kind of add different types of fixtures. So what I did, obviously a fixed geometry, I'll kind of start with the most simple fixture, which is just a fixed geometry. So you can right click here and select fixed geometry. And what this will do is it'll bring up this kind of dialog here. And what it'll do, you can kind of, a good thing with SolidWorks simulation, it'll also give you a little picture of kind of what your fixture is going to do. So when you apply that fixture to that green face there, your part can deflect, it can deform, but that face is not going to be able to move at all. Again, fixed geometry is not necessarily a very realistic fixture. Again, it's used a lot because it's very simple to apply, and a lot of times you can get a close enough result using it. But in most times, if I apply, let's say, a fixed geometry, obviously once I'm in this box, I can just go here, click on this face, and that'll apply fixed geometry. You can kind of see that as well. You can kind of see that these arrows, not only do you have arrows in all three directions, you also have these little kind of circular pieces. That means not only is it constraining displacements in all directions, also constraining moments in all directions. So this face cannot displace X, Y, or Z, or rotate about X, Y, or Z. So pretty much when you do that, that'll fix that face. This is very similar to the example I did last time. So when you do a fixed geometry, again, it's not 100% realistic because typically you're not going to, unless you literally glue a face or you completely, I don't know, somehow bond this face to another face, maybe you completely glue it, then that would probably closely approximate a fixed constraint. But typically you want to make sure, you don't want us to apply fixed constraint, just assume it is. Again, that's kind of when I said last time, you want to go into the, once you run your study, you want to kind of look at what the behavior your part is actually exhibiting. Because once you have that, then you can kind of tell, is this kind of what I'm expecting? If it's not what I'm expecting, maybe this fixture is not completely accurate. So that's pretty much for fixed geometry. Again, there are different fixtures. I'll kind of go through some fixtures real quick. So fixed obviously will just fix an entire face. Again, I can also fix a cylindrical face. So the same idea, the cylindrical face cannot move at all. I could fix multiple entities. So I could technically fix everything here. So a lot of times, and this is kind of one pitfall that people sometimes run into, they will literally just kind of go a little bit crazy with the fixtures. They'll just say, let's just fix, I really am putting a force maybe over here somewhere. Like I'm putting a force maybe on this face right here. Let's just fix everything else. So let's fix this, maybe these faces here. That face goes all the way down there. So you don't necessarily have to go crazy with the fixtures. Typically, the less fixtures you can actually apply, the better. The less fixtures, and obviously get the correct result. If you don't get the behavior you're expecting, then obviously the fixture is wrong, and then you might have to modify it. But you want to make sure you don't necessarily need to fix everything. You want to kind of the way I always recommend to do it is before you actually get into your simulation, kind of look at the part you have. Again, typically, if you may model the part like I did here, most times though, you already have a part or an assembly or something that somebody will send you and say, hey, can you please, do the study on this and tell me if this part is good. Especially in research, because a lot of times you've got people coming in and coming out. So you might have, obviously some research takes several semesters, several years, some big research takes even longer than that, depending on what the project is. So you might have students that maybe either graduate or people are coming in midway through a project. So a lot of times the geometry may already be there. So it's very common for somebody to give you something and say, hey, can you run a simulation on this? So don't assume every time you have to model something. Sometimes you do, sometimes you don't. So obviously in this case, so fixed geometry, yeah, don't try to go crazy unless you absolutely need to. Again, in this part here, obviously we have 6 degrees of freedom. This part can obviously move up and down. So you're it can translate along all 3 axes, X, Y, and Z. It can also rotate. So by applying this fixed constraint here, I've literally eliminated all 6 degrees of freedom from this part. Because one thing, again, like I talked about last time, is you can't, those kind of inertial effects, what that I believe is a 4th assumption for running a static study, is your part cannot just, when you apply a force, your part just can't fly off somewhere. It needs to be able to, it has to be fixed to something, or your assembly. So if you only apply a fixture to one thing, it can still move in another direction, and you apply a force that's not restricted by some sort of fixture, your part will just fly off somewhere and your study will just instantly fail and say, yeah, sorry, can't do it. It'll say your part is either not, it's not constrained properly. So that's for pretty much fixed. Fixed is pretty much a simple one. Another one that you'll see people, I'll try to go through most of these. So next one is roller slider. This is also a very common one. So roller slider is, again, if I apply it to a face like this, what it'll do, kind of like the picture here, kind of like that roller constraint I kind of demonstrated in 2D. This will allow this face, so this body here, or this part, can actually slide on this face, but it cannot penetrate through this face, and it cannot come away, if that makes sense. So it can kind of like the picture here. So those 2 faces are always coplanar, but it's free to move, it's free to translate, and also free to rotate about that face. So a roller slider is typically it's typically a constraint or a fixture that complements another type of fixture. So typically with a part, you're not just going to put one roller slider and just call it a day. It's just not going to be constrained completely. Any questions about fixed geometry or roller slider so far? Okay. So these are the simple ones. Fixed hinge. Again, I'm gonna kind of go through these a little bit quickly, but once we start getting into running stuff, we'll probably, again, we may not use all of these, but at least some of them. So I'll go into more depth of kind of how to define something. So for a fixed hinge is pretty much it can rotate about a cylindrical face. So if I did like a fixed hinge, let's say maybe on this face right here, this entire part can just rotate about that, pretty much the axis of this cylinder. Again, this is not a fixture you see like a lot, but depending on the geometry, sometimes you will need to use something like this. So if we go to advanced fixtures, again, if I get out of fixtures and go back to fixtures, right click on fixtures, you can go to advanced fixtures. So there's some that are here by default. If you go into fixed geometry, let's say you want a roller slider and you hit fixed by accident, that's not a problem because when you go into fixed, that's the default that's selected, but you can always change it. You can also go to advanced and put a different type of fixture. Another fixture that is, I would say pretty common is what's called use reference geometry. And what use reference geometry pretty much does is it's almost like a fixed geometry, but it's fixed geometry that you can kind of tailor exactly to what you need. So if I use a reference geometry, if I was doing this part, let's say I wanted to restrict a translation maybe only in one direction. Let's say I wanted to, kind of how I demonstrated that roller slider. Let's say I want to do that roller slider, but I don't want to actually use the roller slider tool. This is just like an example, obviously. So I could use reference geometry. I could select this face. And what I could do here is for the direction, when you're doing use reference geometry fixture, you also need a direction to kind of base your different axes on, because you obviously have 3 axes here that you can restrain all separately. So what you can do here is you can, let's say, it doesn't really matter what face you select. I can just select maybe, I don't know, that face. If I can select it. Because like that face there. And that pretty much just tells you the different directions. It's just pretty much telling SolidWorks pretty much what is the basis of the directions you're defining. So then based on that, these 3 options here can be defined independently. So I can actually, if I select this face right, or this direction, I can put a 0 displacement, and you can look and obviously look at the arrows and figure out which way they're going. So this would be the same as a roller slider. When you put a displacement of 0, that is that's essentially of restraining all translation in that direction. Another thing this is also very, very useful for is a lot of times, especially when you have a part, sometimes you don't know the actual force that's applied to a part. You know how much it deflects, though. A lot of times you get that with strain gauges. So if you have a strain gauge, and that strain gauge, you can obviously calculate the displacement from that. So when you have that, you can actually specify a certain displacement in place of force. So the good thing with this use reference geometry, this can also kind of double as not only a fixture, but it can also double as kind of a load indirectly. And again, you can do this in all 3 directions. You can do them. So 0 means no displacement. So if I add all 3 of these, this is the equivalent of doing a fixed constraint, but it's not constraining any moments. It's only constraining translations. So that's why you can tell from these arrows, you don't see those little circular or those little cylindrical areas on the end of the arrow here. You only see an arrow, which means it's only constraining a translation. So when you have that, pretty much this can be very useful, especially if you're just trying to constrain motion in one direction. Let's say if you only want this part to be able to move in let's say if I'm looking here, and if I turn this around, only wanted to move in the X direction, I could literally go to maybe this face, and I could constrain, let's see if I can get that. I could constrain those 2 directions. I can constrain Y and Z. And then leave X open. So now it'll be able to slide back and forth, maybe because I want to, I don't know, maybe I have a roller slider already put there or something. Again, there's different ways that you can kind of assign these. Any questions on fixed or on use reference geometry? Okay. So very similar to use reference geometry, there is also on cylindrical faces. So on flat faces, this is also very similar. to use reference geometry. They just kind of use reference geometry is usually when you just want to define a certain direction, kind of like I did use that face. So it's defining all the directions with that face in mind. So on flat face is very similar. You select a face, but in this case, there's really no direction. It's just basing the directions off of this face here. So again, you can do pretty much the exact same thing. Again, I'm not going to spend a lot of time on this one because it's very, very similar. It just kind of, you define it a little bit differently. On cylindrical faces, it's very similar to on flat faces, but as the name implies, it's used for, if I right click and clear this, it's used for cylindrical faces. When you want to constrain a cylindrical face, let's say you don't want, so you can do like radial, meaning this face cannot deform in the radial direction. Maybe you have some sort of insert here. You have something where maybe you have a bolt and you're just going to treat that bolt as a rigid body, meaning it can't deform. So you could do radial, you can do, what is it called? Circumferential, which means it can't rotate. So let's say you want to stop this part from rotating. You could do a circumferential constraint on different faces. And you can also do axial, I believe is this one. Yeah, axial, which means it can't move this way or this way. This axial is a good one for if you're trying to do, let's say you have two, think of a good one. This may be something we may use for the fluid viscous dampers project, is when you have, let's say, a damper or with a spring, and you have, let's say, two, let's see if I can try to annotate actually in Zoom here. So let's say if you have two, I'm gonna try to draw this kind of in 3D. If you have two cylindrical faces, and let's say you have a spring kind of going in between them, and you're trying to maybe analyze the spring or whatever, but you know that this face right here is always concentric with this face because you have maybe a rod or something going down the middle. You could literally put a what is it called, an axial constraint on that face, or oopsies, let's undo that real quick. Put a axial constraint on this face and this face, assuming they were lined up originally, and that'll always keep those in line because they can only move on their own axis. And if their axis is common when you start out, they'll never vary from that axis. So that's one way of doing that. So that's that. Let's see what the other one, on spherical face, again, it's something similar if you have a spherical face. So those are the main, kind of the main constraints. Again, I'll go into a little bit more of these later if anybody has any questions about them. For now, I'll start off with I'll go to standard and just do a fixed constraint on this face, because that's kind of how I had it in the example from last time. So I'll do that, and I'll go ahead and hit accept. So now here, under the fixtures, you're going to have all your constraints. So right now I only have one constraint, that fixed geometry, and that's going to fix this face. So right now my model is completely restrained. I don't have to really worry about it moving anywhere. So any questions about fixtures in general before I move into external loads? Okay. So then when you're moving into loads, so loads are pretty much like fixtures, but you're actually applying a load instead of fixing something. So again, with loads, I'm going to probably talk about, for now, maybe just force and pressure. Maybe I'll talk about torque, but there's a lot of different loads. Again, as we need them, I'll go ahead and kind of go into them because I don't want to kind of bore all you guys with going through every single load that we may or may not use. Most simple is just a force. So you can go to force. And now when you're dealing with, and this applies to fixtures as well, you don't have to apply a fixture just to a face. You can also apply it to an edge. You can apply it to a vertex, which you can apply it pretty much to anything. Again, depending what you kind of apply it to will kind of depend on how the model behaves. Like if I only applied that fixed geometry to this edge right here, obviously this face would still be able to, this bottom part of the face would still be able to deflect because it's not fully fixed. Only this edge right there would be fixed. So that's also another thing to kind of keep in mind. So for forces, obviously, you're all probably very familiar with forces. I can apply a force kind of, I think on the example I had, I applied a force to this face here. And one thing here, so you just by clicking the face and apply a force. One thing here, if you notice, I don't want the force going this way. I actually had the force going in the kind of downward direction, which in this case would be the negative Y direction. Looking at this little triad here, this is another very useful thing to look at. I think I had like 1,000 newtons or something. Again, I might have to change the force because I don't know. So we got 1,000 newtons. And again, if you need to change units, you can switch between SI and the English system if you need to. One thing here though, so by default, when you're applying a force, the default is just normal to the face you select. or the normal direction, which is going to go normal to that face, which is obviously that way. Again, if you need to reverse the direction, you can always reverse it. Let's say I do want it going normal, but I want it coming out. You can just reverse the direction one way or the other. The next thing is what you can do is do a, what's the word? But in this case, since I want it going down, I want to do selected direction. So I can do a selected direction. I can maybe select this face right here for the direction. And similar to fixtures, you can just kind of define different ones. You can just kind of click through them and figure out which direction you're actually trying to go for. In this case, it's probably going to be this one. It's the normal direction of this face. And now my arrows are in the downward direction. One thing about forces, so when you apply a force of, let's say, I think, and obviously it got rid of my 1000, so I'll go and put the 1000 newtons. Again, this is also good if you don't have a force in, let's say, you have a force in several directions. So maybe you have 1000 newtons going down, kind of remember from statics. Sometimes you'll have 1000 Newton, or like you might have a certain force that's going down. You also have another force that's going in, let's say, the Z direction. You can also apply several, all within one force. You can apply a force in different directions to the same face if you have several forces acting on it. So in this case, I only have my one force. So that's all I really need to do. When you have a force, though, it is going to apply a force proportional to the area. So it's going to pretty much calculate the area of the face, and it'll apply a force equally on that entire area. So you can do that and go ahead and hit accept, and that's going to pretty much do your force there. Again, you can kind of hover over the different forces and kind of look at what you have. I think we might have a question. Okay, somebody has to drop off. No worries. Okay, so we have that, and then let's see. So we have that so far. So then for pressure, I'll just kind of go over pressure briefly. Pressure, again, and force are fairly similar. Again, they're just defined in different ways. So I can also apply, let's say I want to apply a pressure, let's say to that face. So pressure, you're going to put your pressure obviously in the units of pressure, and it's going to pretty much what SolidWorks simulation will do is it'll calculate the area of this face and obviously the pressure you apply, and it'll pretty much very similar to applying a force. But again, so a force or a pressure, they're just defined in different ways. A force, you're kind of putting a force on that face, and it's kind of, you can kind of think about it converting between force and pressure. Like that force I applied on this face, it'll take that force and kind of divide by the surface area of that face, and then that's how you get pressure, or vice versa. So it kind of depends on the units you have. Do you know you have a constant pressure on a face, or do you know you have a certain force? Let's say if you have an object sitting on this face here, then yeah, maybe you'll have, you might know the object weighs, I don't know, weighs, or it's applying a force of 1000 newtons, and you can put it on this face type deal. Again, torque, I'm not going to go into torque right now, but torque you can apply to a face, and it's pretty much you're applying a moment. So if you have a force, or if you have maybe you've gone through statics and you've calculated a lot of this stuff by hand, and I have all these forces acting on the system, and then if I calculate them all together and do a sum of moments, I know, I have a resultant force here, and I have a moment maybe on this face about wherever, or I have a resultant moment on this face of whatever. You can kind of apply that with a torque. Again, for this example, I really don't need to talk about it too much, but we'll probably get into that a bit later. So any questions about fixtures or loads? Okay. And again, with loads, you don't just need to apply one load. You don't have to apply one load. You can apply as many loads as you want. Same thing goes for fixtures. So you can apply 10, 15 loads if you wanted to, if you have a complex system that you have a lot of different things going on. Okay, so now that we have that, I'm gonna go ahead and save again. It's always a good idea to kind of save in SolidWorks. So the next step is going to be the mesh. So I talked a lot about mesh last time. So when you go to the mesh, typically what you'll do is you go to create mesh. So when you go to create mesh, actually, before I actually go to the mesh real quick, I will go right click on this kind of the actual geometry here again. And I talked about shell versus, I think I talked about beam elements and different things. So when you do a, what is it called? When you do a simulation, you can treat it as a beam, or if you have the option to treat it as a shell or treat it as a solid, you can do that here, and that's going to kind of vary what mesh you're going to end up getting when you actually go to your mesh parameters. You can also make a rigid part. So again, if you have a part that maybe you don't really care about analyzing any deflections or any stress, you just want, maybe it's a connector from one thing to another. You just want to make it rigid, meaning it doesn't deflect at all. You can kind of do it from there as well. Again, it's not really realistic, but if you're trying to simplify your analysis by a part that does not really, it's so big compared to the rest of the part, or the rest of the assembly, maybe it doesn't really affect much. That's another way you can kind of simplify your analysis. You can also exclude the part completely from the analysis if you have certain components that maybe you don't want to use. Okay, so now we go into our mesh. Again, this is going to be a solid mesh, just kind of based on the geometry we have. So when I go to, and for a shell method, shell mesh, if I can speak, a shell mesh, it needs to have a constant thickness. So why it's going to be kind of hard to treat this as a shell is we have a fillet here. If I had a corresponding fillet on the other side, that was, you had a constant thickness, then you could treat it as a shell. But it gets a little bit more challenging to treat it as a shell when you don't have a constant thickness. Okay, so getting into the mesh, the first thing you'll do is go to create mesh. So when you go to create mesh, this is kind of the general settings you'll have. So when you're looking at the general settings, you can just kind of do the slider if you just want to kind of stay you don't really want to dive into a lot of the details. You can kind of slide it, go more coarse, go more fine type things. Or if you need to get a little bit more advanced, you can go under mesh parameters here, and you can kind of do different kind of mesh, different ways of meshing. The default for SolidWorks is this blended curvature-based mesh. You can also do a standard mesh or just a regular curvature-based mesh. So in this case, since I have this curve, the curvature-based mesh will probably be a little bit better. But again, you can always modify these. You can also modify the size of the elements. You could do the maximum element size, the minimum element size, and then there's some other things here. You can, for curvature-based meshes, there's a minimum number of elements in a circle. So pretty much if you were to kind of continue like a circle around like this, let's say fillet, how many elements you actually want to have around the circumference of that circle. You also have a growth size ratio. So pretty much from one element to the next, how much bigger can it get? Because you don't want to have like a tiny element here and then you have some huge element up here. Again, a lot of this stuff you may or may not need to really worry about when you're running simulations. It's good to know that it exists if you're having issues or if you want to kind of modify something, you can. So right now I'm just gonna leave everything at the default and go ahead and just hit the green check here, and that'll generate my mesh. So it generates the mesh. This is kind of the mesh we're looking at here. So again, it looks like I have 2 elements across the thickness here, which is not bad. It would be better to have maybe 4 or 5, but again, for a kind of like a preliminary study, it's not too bad. Again, if you're going for a more accurate study, yeah, it might be better to have some bigger mesh, or sorry, not bigger mesh, have a finer mesh with more elements. So that's what your mesh looks like. It's always good to kind of look at your mesh and just kind of look at it, make sure everything looks good. Another thing, obviously check how many elements you have across. So again, you can make it finer, you can make it coarser, depending on what you're dealing with. Another thing I will talk about a little bit in mesh, there is something that's called mesh control. So let's say, let's see here. Actually, I'll run this study first and then I'll come back and talk about mesh control. So basically, once you do your mesh, then what you can do is when you have your mesh and you have all of your loads and everything, you're pretty much good to run your study, assuming obviously your part is constrained properly, but in this case, I know it is. So at this point, you can run your study. And so I'll run this study and then I'll kind of go back and I'll kind of use the same part, but I'll kind of do different things with it. So you can kind of see different applications of kind of doing different fixtures and different things. So the next thing you can do is to run a study, you can do one of 2 things. You can either come all the way up to where it's a static one or whatever your study is, right click and say run. You can also do run the study right here. Another thing you can do is if you're doing a mesh, and let's say whatever mesh parameters you used last time, let's say you already ran a study or you're going to, you can create a mesh, or you can also do mesh and run. If you already have a mesh, or if you just wanted to use the default parameters, it'll mesh and run it at the same time. Again, starting out, I would recommend doing the mesh and then going back, or create your mesh and then run it your study separately. But that is kind of a shortcut once you get a little bit, if you want to kind of speed up the process a little bit. So from this point, I'll go and save one more time, and I'll go ahead and run this study. So when you run the study, it'll run, again, depending on the computer you have, how long it takes to run, depending on how many elements you have, how complex the study is, it will vary. This one was obviously very, very quick, but they can vary. So your default plot here is going to be your stress plot. This is von Mises stress, obviously. And so you obviously, by default, when SolidWorks comes pretty much out of the box, it's going to come with 3 default plots. You're going to have your stress, you're going to have your displacement, and you're going to have your strain. So for stress, let's see here. So again, I am well under yield stress here. The yield stress is 2.206. One thing I also a lot of times will change when I'm doing results. So if you right click on a result, you can have some options here. You can edit the definition, which pretty much maybe you don't want von Mises, maybe you want stress in a certain direction. You can do that as well. You can also do shear stress in a certain direction. But in this case, let's say we keep it as von Mises. A lot of times, this is obviously a lot of newtons per meter squared. This is like, I don't know, 40 million, something like that. So a lot of times what I'll do is, and you'll see people put them in megapascals, which is a newton per millimeter squared, or a million newtons per meter squared. So you can do that, and that'll, again, this won't update until you're done with it. So you can hit accept there. Now we're in megapascals. Another thing I'll also do is go to the chart options. Again, this is a bit of personal preference here. So if you like working in scientific notation, then you're fine. Or I personally sometimes find it a little bit confusing. So what I'll do is I'll switch this from scientific to floating. So now I actually just have a value in megapascals. I don't have to actually kind of extrapolate it out. You can also put how many decimal places you want. So you have that. Those are kind of the big ones. Again, you can do these for all of your different studies. So if I go to the displacement plot, I'm not gonna really worry about strain too much here. So if you go to our edit definition again, definition I don't really mind too much. Millimeters is fine. I can also switch to chart options from here, and I'll switch it to floating. And again, there's a way also in SolidWorks that you can go into your defaults and actually change these, so you don't have to do this every time. But if you need to know how to do it, this is kind of how you can do it. Another way you can also do this, or another thing you want to kind of look at, is by default, you kind of see how this part is kind of deflecting. And if you look at the displacement here, the maximum displacement is 0.12 millimeters. And I don't know, just for me, this looks like a lot more than 0.12. The reason for that is you have what's called the deformed result. And if you look here, it'll actually tell you what the deformation scale is. So what this will do is, what it's saying by saying it's 83.3172, is saying that the displacement that's actually occurring, the picture it's showing here is 83 times the displacement, the real displacement. So it's a way to actually visualize how it's displacing, how it's deforming. But this is not actually how your part's going to look. If you actually want to see what the actual displacement is, you can just turn off deformed result. So that is what your actual deformation is, and you really can't even see that it's deflecting at all, really. Again, it's a tiny, tiny bit of deformation. But so a lot of times, if you see a part that's looking like this, you're like, wow, that's deflecting quite a bit. Check your deformation or deformed result. Another thing also is you can modify how much. Let's say you want to kind of see how it's deflecting, but it's obviously deflection is so small. You can kind of up this deformation scale as well. If you go to chart options, or is it chart options, or is it edit definition? Yeah, under edit definition, you can either do automatic, which it'll automatically do a deformation scale for you, or you can do true scale, which is how it actually is, or you can do user defined. One is obviously true scale, or you can kind of specify whatever you want. So I usually keep this as automatic, and then if I want to actually see the true scale, I'll just toggle that on and off. And again, this also works for stress. So you can kind of do something like that. Okay, so we have that. I'm not gonna worry about strain too much. Any questions so far about anything I've talked about?
I have a question.
Sure.
When it comes to mesh, why do we need to mesh them apart? What do we gain from that?
Okay, that's a great question actually. So one thing, so when you're the general purpose of a mesh, so pretty much I kind of talked about it a little bit last time. So the whole purpose of FEA is, so typically obviously you can go to, like, based on from statics, let's say, or strength of materials. If you just put a force on some face and you put a load, you can kind of get a global parameter of kind of what is happening in the part, or global view. But you're not really going to tell exactly where the stress is all over the part. What you have to do to find that, you would have to do a calculation every place you would want to find the stress. So pretty much how FEA works is it'll actually the whole concept of FEA, or finite element analysis, is you're breaking the part down into a finite number of elements, and the software is calculating stress, displacement, all of those type of parameters at every single element, or at every single node, depending on how it does it. So what it is actually doing is that actually allows you having that mesh and being able to run that analysis on every element of that mesh is actually allowing it to paint this picture for you to actually kind of see how the stress changes. Otherwise, you would end up having to, if you had to do this by hand, you would end up, let's say I want to know what the stress is here. You would have to, do a calculation for the stress there and then do that. So what FEA does is it kind of, versus you having to do them all by hand or manually, it breaks the part down into all these different elements, figures out how all these elements interact with each other, what the stress is, what the displacement is, calculates all of those parameters for you, and then kind of gives it to you in this nice, pretty picture. If that kind of makes sense. Does that kind of answer your question?
Yes, it does. Thank you very much.
Okay. Oh, you're welcome. So hopefully, yeah. So that's pretty much how it does. Kind of how it does it. So again, theoretically, you could do FEA by hand. If you only had like 5 elements, you could, yeah, that's maybe something you could do by hand. But when you're dealing with this, another way you can tell here is this alone. If I actually show, what I'll do, actually, I'll go back to the part and go back here, so I don't have to see the results again. You can also just hide the results here. If I actually go to the mesh, so if you look back at the mesh, if you right click on the mesh, you can also do, where is it called? Where is what am I looking for? I actually want to show the mesh. That's a mesh quality plot. Oh, let's see here. Great mesh. That's actually not, I don't need the mesh control symbols. One thing you can do is you can look at the details of the mesh. So when you're looking here, this is also another good one. You can see how many elements you have. So it's a solid mesh. This is also a good printout, especially if you're trying to put in a report or something. A lot of times in CAE, you probably would have, your professor probably would make you print something like this out. So right now we've got actually 8,170 elements. So again, doing this by hand would be a real kind of nightmare. Also tells you how many nodes. So that's definitely a lot to calculate by hand. Also tells you the element size, kind of, and what the study is. So there's a lot of good information here. Also, how much time it took to actually complete the what is it called? Time to complete the mesh. So if we look here and let me see here real quick. Yeah, so if you right click on the thing, you can actually show the mesh. Again, so what I was going to say, I'm trying to remember. Yeah, so pretty much, yeah. So obviously, kind of going to your question a little bit more is, so these are all the elements, obviously. So when you're looking at them, yeah, to calculate that at every single point. So by hand, you could calculate maybe at that node or in this element or whatever, but to do them all would kind of be a big chore, I guess you could say. You can also go here and do hide mesh. Okay, so if we go back to stress, so you can again show it from here. You can also hide it. So those are kind of the big things for plots. Again, you can also create other plots. And another plot, I think I talked about factor of safety last time. So when you go to results, you can also right click and you can add different plots here as well. So a lot of times maybe you want to have a stress. Not only do you want to have a resultant stress, you might want to have stress in different directions. So you could define different plots in different directions as if you don't want to actually have to what's the word? If you don't have to actually, keep modifying this plot every time, maybe you want to have 3 plots with 3 different types of stress that you can kind of look at. Same for displacement. Let's say you want to see how it deflects in different directions. So for a factor of safety plot, this is another really good plot you can do. So again, you can do for all bodies or selected bodies. I only have one body here, so it really doesn't matter too much. And I can do automatic. Again, you can do your failure criteria here. So I talked about these. So again, when you're doing factor of safety, if you've got a non-ductile material or non-linear material, if you don't have a ductile material, you have a brittle material, you don't want to use von Mises or maximum normal stress, I believe it is. Yeah, you want to use either, actually, no, sorry. You want to use either, if it's brittle, you want to use either more Coulomb or maximum normal stress. If it's ductile, you want to use either von Mises or maximum shear stress, which is MSST, maximum shear stress theory. So you can also set an upper limit to the factor of safety, like how high you want it to go. So let's say if you're shooting for a certain factor of safety, you can say, let's say I'm shooting for a factor of safety of 3. I'll show this in a second. But so when you do a factor of safety, again, when you do this, I'll go to chart options here and put this to floating just to make it a little bit easier to see. So when you're looking here, when you're looking at factor of safety plots, the thing you want to actually look at is the minimum factor of safety. You really don't care about the maximum factor of safety. So like this, I don't know, 1 point on the part, I don't know, has a factor of safety of 1,472,000 something. that really does not tell us anything. We don't really care about that. You want to look at the minimum factor of safety in this case, which looks to be 4.6. So another thing, like kind of what that limit will do. Again, you can also click on your plot here, and you can actually modify the upper and lower limits. Like if you don't want it to go up that high, I can say maybe set this to like 10. And now you can see, that's all the thing, everything that's blue is 10 or above, and then you kind of have the thing from there. So factor of safety really kind of shows you in the part. Again, what the factor of safety is in your industry, it kind of depends. So another thing you can actually do is, let's say, so what I'm doing here is very similar. If I go ahead and reset this, which you can reset to the maximum to automatic, hit accept there. So when you go back to, that's what I wanted. When you go back to edit definition, you can set the upper limit as, let's say, I don't know, let's say 3. So that's again setting the upper limit. Again, what I typically do, I typically don't try to use this. I will actually just turn that off, use the automatic. And what I'll do is I'll just go to the plot itself. And let's say in this case, my factor of safety is, what's the word? Let's say for this application, I want this part to have a factor of safety of 3. So what I can do is I can put, or let's say I want to have a factor of safety of 5 for some reason. So what I can see here is by doing that factor of safety of 5, I can really actually see where my problem areas kind of are. So again, most of this part is fine. Maybe I need to put a bigger fillet, put a little bit more material in there or something to kind of stop that. So but obviously the minimum factor of safety here is 4.6. So again, for most applications, 4.6 is a very, very high factor of safety. I believe one of the lowest one of the industries that has one of the lowest factors of safety is actually aerospace because of the weight. So they have factors of safety. I want to say again, it's somewhere in the 1.6 maybe area. Obviously, a factor of safety below 1 is pretty much, it means your part is just going to instantly break. So obviously below 1 does not exist. That's not a factor of safety. I think one of my professors said that's not a factor of safety, that's a factor of death. If it's below 1, that means your part is just going to instantly break. So that's not so, but typically for most of the applications, you're probably looking at a factor of safety between 2 and 3 somewhere. Again, aerospace, I believe, it's in the 1.6 maybe range. Again, you could look all of this up. Again, it probably depends on the specific application as well. So that's a good factor of safety plot. Any questions about factor of safety plots? Okay. Another thing you can also do, you can also probe. I probably should have gone through that as well. If I go back to the stress, let's say you want to know a specific stress at a certain point. You can right-click here. You can right-click on the plot itself. You can also go up to Plot Tools and hit Probe. And what probe allows you to do is you can just click anywhere you want, and it'll try to figure out the closest node, and it'll tell you what node that is, and it'll actually tell you the XYZ location, and it'll also tell you the value of the stress. So let's say you kind of want to get exact values. You can kind of do that. So you can kind of tell, because again, the colors are great, but sometimes you want to really get an exact value of what you're dealing with. Because it looks like green from here to here, I really can't tell that much difference in the color of green, but it's going from 18 to 28. So, that green looks fairly the same. Again, there's a slight difference, but kind of getting a picture that way. So plot is really nice. You can also export all of these. You can also plot these, just based on the different nodes. Again, if you've got nodes all over the place, it really doesn't help too much. If you're going to try to plot this, what I would do is, if you see if we can kind of clear all of these. If you're gonna plot that, I might do maybe start from the edge and go 1, 2, 3. Let's see if I can move these out of the way. 3, if you're kind of trying to get a picture of how it goes from the edge. Something like that, maybe. Then if you plot it, then you can kind of see the ones we did. Now you can kind of see how the stress is kind of going up. And you could export this to Excel. You could save as, I'm pretty sure you can do it as like a, I'm not sure if you can just save this as an Excel file, but I'm pretty sure you can save it as a comment separated data file or comment separated text. So you can do that. You can also, so you can save it. Save will look something like this. Yeah, you can do a CSV, comment separated values, which is very easy to export into Excel or import into Excel if you need to do anything with that. So that's, plot tool is really, really useful when you're doing stuff like that. Okay, and again, you can do that on pretty much any plot. So you can do that on a factor of safety, you can do it on whatever. Any questions on plots or probing? Okay. So let's see here. Wow, so we're already at 7 o'clock. So I don't want to go too far over. What I'll do, I'll probably do this and do one more study and maybe go for about another maybe 10 minutes. Or if anybody has any questions, we can always go a little bit longer, but I don't want to hold you guys too long. So another thing you can do here is, let's say we kind of do a, I want to do a slightly different study with this, let's say. Let's go and hide this plot here real quick. So what I can do is, let's say I want to have this study, but let's say I want to analyze this part in a slightly different way. So what I can do here is I can either just modify this study and modify all the forces. Again, you can right click here and do edit definition, and that'll modify all of those. But if I want to have that study, and again, this is something you'll do. Oh, another thing actually, before I get out of that, I'll get out of this. If I go to the stress, this is the first thing you kind of want to do to kind of assume. Again, this is a very, very simple study, so you can kind of see the behavior we're looking at. What I always want to do here is right click here and do what's called animate. And you can just kind of pause this, and you can kind of, let's see here. If you stop, this is the number of frames. You can do maybe like 20 frames. That'll give you, again, the more frames, it'll take longer for it to update, but it'll give you kind of a smoother photo. You can kind of speed this up. So that's kind of what I'm looking at. I want to see the behavior of the model. This is a great way to do it, to see that is exactly what I'm expecting. This is fixed. I'm applying a load. This should deflect up and down. So this is a great way to actually tell. Again, you could do like 5 frames if you just need something quick. The more frames you have, the more fluid it looks. You can also save this as an AVI file if you want to, let's say, put this in a presentation or something. That's a great way to do that. So to do that, so then what we have is, let's see. So beyond that, what I'll do is, let's go and hide this stress plot real quick. I'm going to make a copy of the study again, because I don't want to edit any of these. So there's a couple ways you can do this. What I'll do, I'll just copy the entire study. I can just right click on the study and do copy study. And I'll just call this static 2. By default, it'll actually tell you what study it's coming from, but obviously I know which study. I don't really need to know that. I'll go ahead and hit accept. So now, right now, again, if I move this up here, again, it's copied the fixtures, it copied the loads, it copied any mesh parameters or anything, it copied. So it copied pretty much everything. It also probably copied the results as well. Yeah. So in this case, let's go, let's do a slightly different study here. Let's say we have, let's see here. Let's see what the easiest way to do this is. Okay, let's try something more along the lines of, let's try something along the lines of this. So let's go to our fixed constraints. Let's delete our fixed real quick. I'll keep the load as the same. But let's say, since we have these holes here, let's say this is maybe bolted to something. And this is actually a really nifty way to kind of do things like this. So one thing we can do here is, let's say I have a bolt, and let's say that bolt, let's say it's like a socket head cap screw that has a round head. So let's say we bolt this into a rigid wall. Because obviously that fixed constraint here, if this is bolted to the wall, it's not going to be 100% accurate. It may be close enough to kind of get us the results we're looking for. But it may not be exactly what we're trying to do. So one thing I will do is, if I go back to features, this is something you kind of want to do in the part environment. I'll actually keep that up there, and I'll switch over to the model tab, which is here. So what I'll do here is I will do a sketch on this face here. And what I'm trying to do is I'm trying to get a face, because right now I don't have any face where that bolt will actually contact, where I can actually, do something like that. There are some connectors and stuff you can do in simulation, but I don't really want to get into connectors quite yet, because I don't have a lot of time right now, but I'll get into that later. So what you can do here is, you can, if you go to features or whatever, you can right click here, you can do a new sketch. And what I'm going to do here is I'm going to just do an offset entities of this, or let's say, actually, I'm not going to do offset. Offset entities is a very nice tool if you know how much you want to offset from a certain edge. So you can just do that and specify a distance. But let's say I actually know, let's say I'll put a couple circles here. Let's say I know the head of the bolt or the head of the screw or whatever. Let's say it's this. I'll go and put 2 circles here. Again, I'll do an equal relationship between these two. So hold down Control, select both of them, hit equal. And you can either do it from there, you can do it from that little flyout thing. Let's say I know the head of these bolts are, there we go. Head of this bolt is, let's say it's, maybe it's a 1-inch head. Let's say it's a 25mm head or something. Something like that. Okay, or maybe you have a washer and then you have a hex bolt on top of it. So the washer is maybe applying the force or whatever. So if you have that, a very nifty feature when you're doing this is there's a tool here, and this is not something that you'll usually learn in graphics, depending what class you take. Maybe if you go up to advanced graphics, you might see this. So there's a nifty tool under curves here. There's a tool that's called split line. And with this tool, this is very, very useful. Two applications where this is very useful is when you're doing appearances. So let's say you want to have like a logo or something on a part, you can actually sketch out your logo and then you could do a split line. And what split line does is it's going to split a face or faces into multiple faces. And you kind of see what I'm going to do here. The one I usually use is projection. So what I can do here is so go to projection. I'm going to, obviously, the selections is going to be my current sketch. I want to use this sketch. I want to project this sketch onto this face. So the face I want is going to be that face right there. And I'll go ahead and hit accept. And if you notice what has actually happened now is you actually have you've got several faces. You have a face here, and now you have these two faces here. So this is great if you want to put appearances like on specific faces. If you have a logo, if you have something like that, you want to go to appearances and you want to go to maybe plastic, medium gloss or something. Maybe you want to put a red appearance, on if my thing is actually working, or I can actually do this. Do appearance and kind of, maybe we're gonna that's actually not what I want. You can, my thing is not actually showing up for putting appearances, but yeah, you can do an appearance on different faces here if you want to. Another thing is very useful is for simulation. So if you need to apply a force, if you need to apply a fixture to a certain part of a face, like the one I'm kind of gearing up to do right now, this is actually a very good, what is it called? A very good way of doing it. So what we'll do here is I will do this. So let's go back to our static 2. And let's actually go to static 1, make sure nothing. Yeah, static 1, since we actually changed this face, again, this would not really change much on static 1. I could actually just do, since I did kind of change a little bit of geometry, I can go here. This is where you do a mesh and run, to remesh it and run it again. Again, nothing, I don't think anything really changed there because I didn't change anything. But if we go over to static 2, now what we can do is, so for fixtures, if I have this, let's say it's bolted to the wall, what I can do here is now when I go to my fixtures, and let's say the load is the same. So if I go to my fixtures, what I can do, let's go to fixed geometry. Again, I can kind of fix these different ways. So let's say a very simplified, what's the word here? A very simplified way. You could either fix the inside of these faces right here, or like these faces. You can either fix them. So obviously you've got a bolt going through it. Again, you can get very, very complicated or very complex of how bolts actually interact with holes because there are different constraints, but on a very simplified scale. But what I'm going to do here, I'm going to kind of use some of those ones I was talking about earlier. So what I can do here is I'm going to go to that on cylindrical faces dialog. So what I'm going to do is I'm going to so I'll go to on cylindrical faces. I'm going to select both of these faces. And in this case, what I want is I don't want any, what is it called? I don't want any axial displacement, if that kind of makes sense. So I don't want these to kind of move back and forth. Actually, let me think, let's see, actually, let me see. Actually, it's radial is what I actually want. So I actually want radial. So I don't want these holes really to deform. We're going to kind of treat this as it's a rigid bolt. Nothing's really deforming. Again, this is where simulation can get very tricky, is when you start getting into getting accurate constraints. But so I'll do something like this. Again, I'll put 0 to make that fixed. So now what's happening right now is we have these that can't really deform in that direction, but this part can still kind of slide around. These holes can't really deform, but so what I want to do here is I want to actually do something with these things. So again, a very simplified approach. Again, you can get very, very complex with these. I'll add another fixed, and I'll just do a fixed geometry to these faces. Again, I could be very simple and just put a fixed constraint on these holes as well. And actually, maybe I'll do that just for simplicity's sake. So let me just delete this on cylindrical face and say yes. And go to fixtures and go to fix, and I'll just fix this face, this face, this face, and that face, let's just say. So kind of what you would assume. Again, if you have it against a wall or something, maybe you want to do a roller slider or something on the back here. But maybe you're afraid that this part might come off of the wall. So you want to kind of see kind of how that, kind of what the results look like. So just do something like that. So now I'll save that. So now any questions about kind of setting up this model or this analysis. Okay. So based on that, what I will do is now from here, obviously these are all fixed, so this should be fully constrained. Now what I'll do is I will do a mesh. Now, one thing with the mesh, unless you change the geometry, you really don't need to remesh. So what I could do is, let's say this geometry has not changed. I could, and I just change fixtures or loads. I don't technically need to remesh, but since I did do the split line, these faces are now different. So I will just go and remesh. Again, I'm just gonna do another mesh and run because I really don't need to. I don't really need to go into much. I don't have to really change that much of the mesh. So what I'll go here is, let's see. So I'll go ahead and just do a mesh and run. Kind of see what our that'll mesh. Okay, so let's kind of see what we're dealing with here. So now obviously it looks a little bit different. So let's go see if we can go ahead and animate this. So now if you notice here, it's kind of almost like a hinge. So this is kind of hinging back and forth, whereas before when this entire face was fixed, it could not move at all. So these are a lot of the things you kind of want to look at when you're looking at a study, specifically a static study, is kind of how it is set up. Because when you're dealing with fixtures, if your fixtures are wrong, a lot of times I would say the fixtures are a lot harder than the loads. Because the load, a lot of times, this is sitting on this or it's supporting this amount of weight or whatever. But when you're dealing with fixtures, you just kind of want to make sure your fixtures are in the right thing, especially if you have something that's bolted. Because now, if you notice here, I don't have any stress concentration here anymore. If I kind of get out of this, my stress concentration now is right here. So obviously you can tell based on kind of how you, and if we look at our factor of safety, okay, so now we got a factor of safety. Now the factor of safety has actually dropped. And again, you may around here, this may honestly be a stress concentration because of these fixed constraints. That's another thing you have to be careful with fixed constraints. Right around it, since it can't move at all, you can kind of get a artificially high stress. But that is definitely something to look at. If you notice here, even in this area here, now we have even if we negate or neglect the kind of the ones in the 2 range, now we got a factor of safety of like 3 in quite a bit of the part. When before we had more of a factor of safety, I think there's only a little area here that was not kind of a factor of safety of like 5 or above. We can kind of switch back and forth so we can kind of look at both factors of safety. So right now, everything is pretty much a factor of safety of above 5, except this little area here. This now, if we go to our factor of safety plot, you still kind of have that little bit of that little area here. But now if you notice, our results look quite a bit different now. You've got a lower factor of safety in a much bigger area of the part. So this is where I can't stress enough that knowing kind of, or being very careful with how you do constraints, how you set up your study and the accuracy of your results can be, very, what is it called? Can be very beneficial or detrimental to what you're analyzing. So again, it's always good to maybe run some calculations by hand, maybe stress at a certain point and try to compare it to your FEA. That's never a bad idea. And again, even with these fixed constraints, they're not 100% realistic because again, when you have a bolt and this is sliding down, this way, what will end up happening is this bolt is obviously going to deform this hole here. So what I would actually assume in real life is this hole right here would actually be a very, what is it called? You would actually have quite a bit of stress in this hole, actually at the top surface of this hole because this whole part is trying to go down. But is that hopefully this all makes sense? Does anybody have any questions about this? I know I'm going a little over, so I'll try to kind of wrap it up about now. Any questions about anything in SolidWorks simulation in general, or FEA? Okay. So yeah, that's definitely something. Next time I'm going to try to probably go into a little bit more in meshing with mesh controls. Pretty much if you need a finer mesh, what I'll do, this is the last thing before I'll stop for today. So if you need to adjust the mesh, obviously, one thing we can look at, I'll go to the first study, or let's actually I'll make a copy of, let's see here. Let's make a copy of study 1 again, just call it static 3. This should be pretty quick, but just to show you if you need to vary a mesh. So one thing you can do here is let's say here, so we've got all of our things. Let's say I want to, let's just compare our results here. So our first study, again, that's the one that's fixed on the back. We've got a maximum stress of 47.35 or 385. So let's go to our static 3 and let's do a much finer mesh. And let's just kind of see how that affects things. So again, this would be kind of the process you would want to go through. In this case, I don't want to do a mesh and run. I want to actually create a new mesh. Remeshing, it's going to delete the results. That's obviously true because when you have a different mesh, your results are not going to be accurate anymore. So I go to mesh parameter. Let's just say, let's go all the way up. Hopefully my computer doesn't give me a problem here, but I have a decently fast computer. So hopefully, I'll just crank it all the way up. But again, depending on the speed of your computer and how much time you want to spend, you can kind of adjust, or you can just actually, if let's you go all the way up and you still want a smaller element size, you could literally change that as well. So let's go ahead and hit accept here. Again, this should still run rather fast. So this is just the mesh. So now you can see, now we have, let's see, 1, 2, 3, the 3 elements now across the thickness. So we have 3 elements. So now let's just kind of see, now if I go here and do run. So let's kind of see what we're dealing with here. You can also go to more and you can kind of see how it's running. It still runs relatively fast. So now we got 49.163. Let's compare to before. You can also double click on a plot to show it. 47. So now the stress has gone up by about 2 megapascals. And again, let's just, if we go back to this, let's say I really do a fine mesh. I'm just going to modify this same study. Let's do create mesh. And let's just, right now we're at a maximum element size of 2.88. Let's see if we can, let's see. Let's just kind of crank this down maybe to, crank it down to like 1.72 or something. Again, with meshes, especially if you have a big part, meshes can make your studies take a long time. It's not uncommon for if you have a big thing or a big part or a big assembly, your studies may take hours and hours to run. Again, this is a very simple part, but let's see what a kind of mesh like this looks like. This is probably very, very fine. So this may take a second longer. And then I'll go ahead and kind of wrap up with this. So now we have, let's see here, 1, 2, 3, 4, 5, 6. Now we got 6 elements. So this is a very, very fine mesh. Again, the finer the mesh, typically it'll give you more accurate results. So now if we go here and we go ahead and run this one more time, and you'll see how the study time is actually going up and up as we do this. Let's see if it'll, okay, so if I go to more. So the first study was like literally less than a second, I think it was. The second one was maybe a few seconds. Now we'll actually see how much. So it took about maybe 11, 12 seconds. Now we're at 49. So now if you notice, we're actually converging now. So now between the previous one, still going up a little bit, but you'll actually, once you start hitting a plateau, it should not, if this keeps going up and up and up, then then it's a cause for concern because you may have some stress concentration you may have to modify or something. But right now it started at like 40, if we go to static 1, started at 47. I think the other one was 40, I think it was like 48, 49, somewhere like that. And now we're at like 40, I think it was 49 something. Again, I probably should have copied the study again. Now we're at 49, so it's going up a little bit, but it's definitely plateauing out. So that's good. So that's kind of what you want to look for. So it never hurts to do several studies and kind of make the mesh finer and finer. But yeah, that's kind of with meshes and things like that. Let me save this one more time. That's kind of the stuff to look at. Any questions about meshing or running studies? And I'll probably kind of wrap this up. Okay. So next time I'll try to go over something that's called mesh controls. If you need to make meshes finer in certain parts, you may not want a super, super fine mesh everywhere. You may want to go into just kind of putting a mesh in just certain areas. So that's what I'll kind of go into next time. But yeah, if anybody's have any questions, I will go ahead and stop recording now.
I had a quick question about the
Oh,
factor of
sure.
safety.
Sure. Before I stop recording. Okay.
What does I'm guessing this is all dependent on how good your model is, assembly is, and your constraint fixtures.
Mhm.
But how does SolidWorks calculate the factor of safety, and how much can we trust it?
Okay, so that's actually a very good question. So pretty much how it calculates it is kind of from if you look back at the last video, and I'll try to do this because I don't have my notes up in front of me, but so obviously the formula for factor of safety is pretty much it's the allowable stress over the actual stress. So if pretty much typically you want if the allowable stress is, let's say, I don't know, let's just say it's 500 psi and your actual stress is 100 psi, obviously there would be a factor of safety of 5 or be 500 or 100. So what it'll do is, again, depending on what your failure theory is, it'll calculate it based on that. So what it's doing is how SolidWorks actually calculates is when you go to your stress, how it calculates the factor of safety essentially is kind of a simplified thing, but what it'll do is obviously it's calculating the stress at every portion on this model. it knows what the yield strength is if you have a material that has a defined yield strength. What it'll do is it'll take literally at every element or every node, it will literally take your actual stress and it'll divide it by the yield strength at every point. And then based on that, it'll obviously get a value. And then that value is what your factor of safety is kind of at every point, if that kind of makes sense. Hopefully does it kind of answer your question? I'll go into a little bit more.
Yeah. So the
Okay.
allowable stress comes from the material that we choose at the beginning, and then obviously the stresses that are applied to it.
Correct. Yeah. So the allowable stress would be based on the material. That's going to be a material property. And then the stress that you actually have in the like induced by whatever load you're applying, it'll take the allowable stress divided by the induced stress, and then that'll calculate your factor of safety at every point. Another thing also with factor of safety, I'm trying to think, I just lost my train of thought, but so with factor of safety, what you want to do is, again, every application, you're going to have a certain factor of safety you want. A lot of times also, a kind of a misconception with factor of safety is everybody thinks a huge factor of safety is necessarily better, and in a lot of ways it may be, but especially when you're dealing with products or dealing with something, you don't want to, if you don't necessarily need a factor of safety of 100. A factor of safety of 2 to 3 in most applications is plenty.
Yeah.
Again, it depends on the application. So a lot of times what you'll see people do is they'll use a factor of safety plot, and what they'll do is, let's say they have this whole thing that's now 5. Let's say I'm shooting for a factor of safety, let's say 3. What I can do now is I can know this bracket. Maybe I can go back and actually modify this from, I forget how thick I made this. Let me actually go back to the model here real quick. If I go to this, 10 millimeters. So instead of 10 millimeters, maybe I can do this as 5 millimeters. So you can kind of play with your factor of safety and your geometry. And this is kind of where I was kind of talking about before, where you're kind of going between CAD and CAE, or between, SolidWorks, like modeling a SolidWorks and your simulations, to keep modeling and analyzing and kind of refining your model to get a good factor of safety of what your application is, but you don't have an extremely high factor of safety in any areas, and you obviously don't have a low factor of safety.
Yeah.
If that kind of makes sense.
Yeah, that makes sense. My professor was telling me, like, if you have a really high factor of safety, you're probably over engineering whatever
Right.
part you're
Correct.
making. You're probably
Yeah.
costing money.
Right. Yeah, you're costing money. Right. So that, yeah, definitely, because again, it's more, and again, this kind of depends a lot. Again, some industries may not, when it comes to factor of safety, it may not be as crucial. Like a lot of times, one example is it depends on how you manufacture the part as well. Again, if you have, let's say, what is it called? Let's say you're trying to machine this part out. And again, you can sometimes, a lot of times you'll see parts and they'll have kind of a design, they'll cut out different things. You'll see like a kind of a hexagonal pattern to kind of remove material and reduce weight. So obviously that will cost machining time. So let's say the thickness is the same. Let's say for some reason you can't change the thickness. That's just the design application. So a lot of times they'll start, removing material. They'll put, cutouts or something. But a lot of times those cutouts actually, will cost money to actually machine. It takes longer to actually machine it. So your stock or whatever it is going to be the same. Let's say you're using like an angle stock or whatever stock you get. Let's say it's let's say it's just a bar stock or something. So in that case, you may not really care that the factor of safety is high. You might say, more factor of safety, unless obviously weight is a factor. But let's say it's just a bracket that's going to mount on a wall. You really don't care if it weighs a little bit more. You're not really, the amount of material, let's say the stock you can get is, let's say, this shape, exactly the shape. So you can remove more material to reduce weight, but it's really not, in that application, it's not really helping you. It's actually costing you more money because the material is going to be the same, but you're actually having to remove more material by machining.
Right. It takes longer.
It takes longer. So some applications, you'll have stuff like that where it may not matter too much. Again, the part may be a little bit over-engineered. So you might think, well, maybe can I get a thinner, stock? But let's just say for the sake of argument here that that's the only stock you can get, that's the only stock they have, that's that material that you need. Then yeah, again, you could put those cutouts there, but again, that's costing more money. Another thing also is, but depending on the manufacturing, let's say you're 3D printing something. Yeah, if you're 3D printing something, obviously it's additive. So you're obviously adding material. So the more material you have, the longer it's going to take, the more it's going to cost. So something like that, then you definitely want to reduce material and, weight in those kind of, so yeah, like what your professor was saying, but I'll kind of go a step further. It depends highly on what you're doing.
Right.
It depends on how it's manufactured, what kind of material you can get, type of deal. And again, it depends on, like aerospace. Yeah, it's always weight is everything. So in that type of application, you're always trying to save weight, because I forget what it is. I think there was some figure I heard. Again, you could probably look this up, but it was like every extra, I think, pound, like on an aircraft, I think over the life of that aircraft, I don't know, costs like, I don't know, it costs like $1 million or something in fuel per pound or per whatever. It's
Oh,
some
damn.
insane number. Yeah. So it's
Yeah.
definitely, so with applications like that, yeah, weight is like everything. Even if the part costs 10 times as much, and if you save a pound, you're going to get the savings in the long run, assuming that part will last the length of the aircraft. So yeah,
Mhm.
that's with factor of safety. It kind of depends what you're looking at. But yeah,
Yeah.
in general, yeah, you don't want to over-engineer the part. You don't want a factor of safety that's way too high. You don't want a factor of safety that's way too low. Especially if you're doing with weight, you're going to want to kind of go in and maybe make some cutouts, do something to kind of remove material and then reanalyze it and kind of keep looking at your factor of safety until you can kind of, and that's kind of where the engineering part comes in. It's kind of that back and forth between CAD and simulation.
Okay. Interesting.
But yeah, so that's definitely that's a great question though, because yeah, factor of safety. Again, I just came up with numbers for this simulation. So yeah, obviously, I think we had like one part of the part was like a factor of safety of like 1.2 million or something. Yeah, obviously, if you're getting a factor of safety that high, yeah, no, you don't. If you got a factor of safety like 1 million, then you're using something way too big, or I mean, I don't know.
Yeah.
Or yeah, something's wrong.
Yeah, it's not very wrong.
Right, but yeah, that's definitely kind of that. But does that kind of hopefully that answers your question?
Yeah, I answered it perfectly.
Perfect. Okay, so I'm gonna go and stop recording because I don't hold you too much longer. Let me stop recording here real quick. Stop